morning, Alan. Welcome back. Good morning, Nadina. Hi, Jordan. Welcome back. Joey, welcome back. Good morning. Good morning, John. Happy Friday, Emma. Hey, Faith, welcome back. Good morning, Wendy.
Hey, Mr. Brown.
Hey, what's going on, Joe?
Nothing. How are you?
Not too much. Just having fun out here in my Zoom room. Thanks for asking. Hey, Jumila. Welcome back. Good morning, Santino. Hey, Michael. Welcome back. Good morning, Cam. Welcome back. Hey, Nidal. Happy Friday. Crisscross. Joseph. Welcome back. Good morning, Irvin. Happy Friday. Frank. Hey, Ryan. Welcome back. Hey, Alex. Thanks for coming on time. Welcome back. Hey, Phil. Good morning, Phil. Hope you're doing well. Good morning, Bellman. Hey, Leonardo. Welcome back. Happy Friday. That was good timing. All right, welcome back. Sorry for the confusion again with the little stream there. I had to edit that really quickly. It was period 1 and 2. Hi, Kai. Welcome back. So I apologize for I gave you guys a couple extra minutes to get in here if people were still trying to wait in their waiting room for Zoom. All right, happy Friday. Please check the attendance to the left. Please make sure it's accurate, precise. So we can start class for today. Anybody do anything fun this weekend? I got a holiday tree. I don't say Christmas. I got a holiday tree for whatever holiday. And we're going to decorate that today. That's our thing. That's our goal. All right, let's check out the update for COVID for Oneida County. Here's this ugly data chart. I say ugly because it's affecting us in a negative way. All right, there are 4,472 active, not total cases that were resolved. Right now, if we walk outside in the county, there's 4,472 active cases of COVID out there. A lot of people have COVID in our county. There's 132 people in the hospital. There's 18 people, a couple more people from yesterday in ICU. There's 182 deaths. There is now more active cases than resolved cases in Oneida County. It's a little crazy, a little cray-cray. You can check out the death rate for the day, percentage. The daily positive rate, yesterday was a rough day too, this curve. So I'm analyzing this curve from a distance away. I'm gonna check it out so you can see what's going on. Let's see. Hold it up a little bit. So there's a little curve. Don't worry about this thing. That's my guess what the curve's gonna look like. Far checking it out. That's what I see forming. There's a first wave. I don't know, maybe we did plateau. Maybe see it, maybe that's the first part of the curve. I don't think it's gonna be like, I don't think it's going like that, maybe. But what goes up must come down. It's still gonna take a time span to come down. It's not gonna drop off all of a sudden. It's definitely gonna take some time to go through that second span, second hump of the wave. But anyways, maybe, hopefully it doesn't look, hopefully it just drops off with everybody getting the vaccine overnight and then all gone. We'll see. Hi, Micaiah. Welcome back. Oh, Tintin's here too. Hi, Tintin. Welcome. All right, so anyways, there's a COVID little curve there for us. Maybe it looks something like that. Let's zoom in on that again. So zoom in on that, see where we're at for the past couple of days. So there's a second wave hitting us. The 16th, there's 278 cases. So 16th, 2 days ago, Wednesday, there's 278 cases. Tuesday, there's 274. A lot of people got diagnosed with that. So that's just the people that got tested. Not everybody that has COVID is going to actually go out there and say, oh, I need to get tested for COVID. There's some stubborn people out there that just say, whatever it is, I'm not going to get tested. There's 278 people that actually got tested for COVID on Wednesday. Be smart, be safe, take care of yourself, take care of your loved ones, wear a mask, social distance, protect yourselves. All right, let's check out the daily agenda for today. So I had a lot on the daily agenda today, but I'm going to summarize. I'm going to break it up a little bit. I'm not going to do all this for today's class. So today we're going to start off with Happy Friday. Quote of the week comes from Thomas Edison. I have not failed. I've successfully discovered 10,000 things that won't work. The daily agenda for Friday, December 18, 2020. Today's a day 4. Hopefully you had a good day off yesterday. Unit number 5 is chemical bonding. We're finishing up with ionic bonding today, maybe one more class. We're going through percent composition of hydrates for today. We started it. We're going to go through it a lot more detailed today. We'll start off with a warm-up. After the warm-up, we will go through some guided notes. We'll watch a YouTube video on how to do a laboratory experiment on percent of a hydrate. We'll go through some examples, and then you should be able to do the exit pass on topic 6, which is percent composition. So that, I know there's a couple questions on hydrates where you can't do it, at least one question on a hydrate. That you should be able to complete at the end of today's class in full detail. That is due by tomorrow, so don't forget you have a couple exit passes due by tomorrow. You have topic number 5 and topic number 6, which are due tomorrow. You do not have to, so this, I'll make this extend beyond further. You do not have to do the warm-ups. They have to be completed or submitted. They're not going towards your grade. But topic 6, this is an exit pass. That will go towards your grade. And so will the exit pass on moles. So please make sure you do topic 5 and topic 6 exit passes. All right, let's start off with the warm-up for today. So the warm-up says 12, 18, 20, warm-up. There's only a few questions here for this warm-up. but they do take a little bit more time. So it starts off with 12, 18, 20 warm up. What's the total number of moles of oxygen atoms present in 1 mole of MgCl032? You have another question on total number of moles, and the last question is on percent composition. So I'm breaking it up, adding different topics to the warm-up for this one. So there's 3 questions. They're going to take a little time. I'll give you till 12 o'clock to work on them. At 12 o'clock, we will review. Yeah, the vaccine's rolling out, but if everybody gets that vaccine overnight, then if the vaccine's effective, then I'm sorry, Frank. Sorry to jump off, but Frank just messaged me maybe a couple minutes ago, but if the vaccine rolls out and it's effective, then yeah, the curve will drop right down. If it's not effective, then I'm sure it's going to be effective. If it's not effective, then obviously it's not going to affect the curve much. So we'll see what happens there. So at 12 o'clock, I will review the warm-up. So please work on the warm-up from now till 12 o'clock. All right, let's check out the answers for questions 1 through 3. Tried some different backgrounds here. Obviously, didn't work out to the left for my work, but what are you gonna do? Live and you learn. All right, question number 1. Question 1 reads: what's the total number of moles of oxygen atoms present in 1 mole of MgClO3 Please put the answer in the chat for question number 1. I'll wait for 10 responses, then we'll go through it. Question number 1, please put the answer. Thanks, Alex. 1 for 1. Thanks, Alan. You're good. Thanks, Zin. Good. Seem good. Thank you. Thanks, Mike. Michael, correct. Thank you. Thanks, John. Irvin, thank you. So yeah, a lot of you guys already know this answer. Question number 1, best answer is going to be choice D. So in this question, let's see here. We're looking at oxygen atoms in 1 mole. Oxygen atoms present in 1 mole of MgClO3 2. That 2 has to be transferred over. So that 2 is going to transfer over to everything in the compound. So 3 times 2, best answer is going to be choice D, 6. If they said how present in maybe 2 moles of the compound, so if it said 2 moles of the compound, then there'd be a coefficient of 2 out in front of that number, or the compound. So that 2 would be there. That's 2 moles. That transfers everything in the compound. And still you have to take the subscript, transfers everything inside the parentheses. So 6 times 2, that would have been 12, if that were the question. All right, let's try another one. Question number 2. Question reads: what's the total number of moles contained in 115 grams of C2H5OH? Please put the answer in the chat. Thanks, Jumila. Thanks, Kai. Thanks, Michael. Thanks, Asim. Kim. Thanks, Alex. Yeah, so I showed you the work kind of over here to the left. You could see the exact unknown values. I did give you the values that were unknown, or the values that came from the passage. Those are right here. So we obviously had number of moles what we're looking for. We had mass was equal to 115, number of moles, and the compound C2H5OH. Those were all given to us. I solved for the GFM. You could kind of read that. Guess let's see a way to get through this. Through this. Kind of. All right, so anyways, you have my formula. It has number of moles equals mass over GFM. Plug on in, we have 115 divided by 46. Hopefully you see my GFM, how you calculate. Hopefully you know how to do that. Choice D is the best answer for that one. 2, the best answer is D. All right, last question, number 3 is a part 2 question on the reagent. So you had to read through this in order to get this one correct. A lot of times, if you read the passage, there's gonna be a lot of key information that comes from that passage. The regents, if we have that regents at the end of the year, it's gonna be 50 multiple choice questions and 35 short answer responses. This is a short answer response. Base your answer to the following question on the information below and your knowledge of chemistry. Baking soda, NaHCO3, can be commercially produced during a series of chemical reactions called the Solvay process. In this process, NH3, NaCl, and other chemicals are used to produce NaHCO3 and then H4Cl. To reduce production costs, NH3 is recovered from NH4Cl through a different series of reactions. This series of reactions can be summarized by the overall reactions represented by the unbalanced equation below. Determine the percent composition by mass of carbon in making baking soda. So they gave you a lot of information in this passage. What they want you to do, they want you to find the percent composition of mass and baking soda. But it also gives you the GFM, baking soda. It also gives you the GFM of the compound. So if you didn't read through this text above, then you're not going to be able to get this question right. This has to be read. You have to read this section right there in order to get it right. If you had to reread it again, you have to find out where baking soda is. You could do that. Baking soda. Oh, baking soda. Now you know what it is. Baking soda, NaHCO3. So that's a compound we love, or we're dealing with. Percent composition by mass of carbon in baking soda. We have a GFM given to us of 84 grams per mole. So again, please, actually, before I go through it, please put your answer in the chats. Please put the answer in the chat for number 3. Thanks, Jumila. Whole number would have been fine. Thanks, C. Thanks, Faith. Thanks, Nadina. Thanks, Alex. Everyone, thank you. Answers I got so far, 14%, 14.3%, and 15%. Thanks, Urban. Let's figure out which one of those is the best answer. All right, so the formula for percent composition, percent equals part over whole times 100. Part over whole times 100. Percent of what? Percent of carbon. How many carbons are present there? There's 1. The mass of carbon is equal to 12.0. The whole is going to be 84. So that's your setup. Part over whole times 100. Now take out your calculator. Let's calculate it. 12 divided by 84. Equals times 100. Don't forget that. So yeah, that rounds up to 14.3. Since this is a whole number 84, 14% would have been acceptable as well. Yeah, if you wanted to put this whole thing there, they'd still give you credit. If you want to write the whole thing out, they'd still give you credit. But it's just going to make you a better rounder in the end if you know these rules for sig figs. So 14 or 14.3 were correct. I'm not sure where the couple of 15s came from. I don't know if you rounded the 12 to something else, maybe. I don't know. All right, so those are the warm-up activity questions. Hopefully you guys had successes. Anybody have any questions on 1 through 3? Want more clarification on any of those 1 through 3? All right, please open up your guided notes. We left off with hydrates. Here we are, this big chunk. I told you this unit's going to take a while. Ionic bonding is probably like the longest unit we have all year. And this whole unit, chemical bonding, ionic bonding is a long time we've been talking about since the 30th, I guess, maybe the 30th. Maybe put the date on a few days later, I can't remember. But anyways, we talked about ions. We talked about how they form. We talked about naming metals. We talked about naming nonmetals. We talked about ionic bonds, how they form, transferring electrons. We talked about covalent bonds. We talked about Leo Szilard, ion formation, electronegativity we talked about, Joseph A's crisscross rule, dancing on the table, properties of metals and nonmetals when they bond. We talked about binary compounds. We talked about naming them, crisscrossing them. We talked about ternary compounds, page 2 of the reference table, and polyatomic ions. We crisscross those. We talked about different types of formulas, empirical, molecular, structural, and ball and stick models. We talked about moles. We talked about GFMs. You calculated GFMs. We talked about number of moles. We analyzed several of them. We also talked about percent composition a few days ago. We analyzed several examples last class about percent comp, and we left off talking about hydrates. So our goal for today is to get through this hydrate, that's spelled wrong, hydrates, and then all these examples as well. So we'll get through those examples, and we'll watch a video, and that's gonna be really about it. It's gonna take some time to really get there though. So here we go. We left off. I'm on page, let's see what page. I'm on page 18 right now. Maybe you're on page 18, 19, 20. I don't care where you are. But we talked about a hydrate. Drew like an atom or molecule of NaCl with water trapped inside of it last time. So hydrates are going to be ionic solids with water trapped inside the crystal lattice. The ratio of water to each mole of the ionic compound is determined by a formula that's similar to this. So that would be like NaCl with a number of moles, and it's going to be like number of moles of water that are trapped within it. So N is just going to be like a coefficient. And I gave you a formula. Great. So the formula we have is percent of a hydrate. I'm going to paint this. Given mass of the water in the hydrate times 100. I'm given mass of the water in the hydrate divided by the given mass of the water of the hydrate. So you're going to be evaporating something in the situation. So we'll analyze an example of that. To determine the percent of water in a hydrate given the hydrate formula, first thing you want to do is determine the formula mass of the hydrate. So you're going to look for the GFM again. All right, steps you want to do, you want to find the GFM, gram formula mass. Not a ton of notes. Examples are going to take a few minutes to do though. So find the gram formula mass. So the gram formula mass is something that you're going to have to know how to do automatically. It's not going to be on the reference table, but the GFM is something you should be able to calculate pretty quickly. Once you find the GFM of the crystals, what you're going to do next, you're going to find the formula mass from the GFM or formula mass of the number of moles of water. So I know this example might be a little bit wordy here for the steps, but once you see an example coming up soon, that'll make it a lot easier to do it. And then the last thing I have to do is going to have to add them together. So you're basically taking the total GFM of the compound. Add the two numbers together. So I can't recall exactly how far we got into hydrates last time, but anyways, a hydrate would be something like copper sulfate. I wish we could do this lab in class, and it's one of labs that really makes sense and be easy to do for us. We use a Bunsen burner, we use a stand. But when you do this lab, if we get back to school this year, we will do this lab. We'll do like review throughout the year, and we'll go through the important labs that I think. But anyways, if we perform this lab, what's going to happen? You're going to have a evaporating dish or a crucible. So this is going to be my evaporating dish or crucible. Just a white ceramic, like a little tea set. It looks like a little teacup, but it's not. It's smaller than that. So it's a small little crucible. And inside that crucible is going to be like a small crystal, like a blue powder inside there. So this would be like sodium or copper sulfate. So inside there's a mass of copper sulfate. And we'll say copper sulfate, CuSO4. And we'll give this obviously we'll put a little dot there, which I'll do after, with H2O. That means it's trapped inside there. So copper sulfate with some water in there. Usually there's like a little dot right there. So copper sulfate with water stuck inside there. If you start off with a copper sulfate and you don't heat it up yet, if it's blue, there's gonna be water stuck inside. So what's gonna happen in this lab is we would take that crucible, we would take that substance inside there, we would put this on top of a ring stand. Here's a ring, oops. Gotta work on my drawing skills here. You'd put that on top of a ring stand. That ring stand would be connected to, or have a Bunsen burner on top of it. So a Bunsen burner. So Bunsen burner be on top. Yeah, so we would be doing this in class. You would be using a Bunsen burner in class as well, but kind of difficult when you're at home. That Bunsen burner would have a little nozzle that comes out, and that would be connected to a wire tube, which would be connected to the lab table where the gas would come from. You don't have to draw this. So that's connected to some sort of tube, has a little nozzle in the lab bench. Once you put it on, once you strike it with a striker or even a match, you would get some sort of flame popping out there. So that flame, wait a minute, let's make this connect on something. It's not just gonna hang out in space. So we do need an iron ring there as well. It's been a while since we talked about lab procedures though. So an iron ring, what that's gonna be, it's just gonna be like a clamp. It looks like that if you're looking at it vertically. But anyways, an iron ring is going to be supported. It's going to be connected here with like a little screw. And then it's going to hold up my ring, goes around. It's going to hold up that crucible. But additionally, if you don't have something to hold on to that, it's going to fall right through. So on top of that would be something called a clay triangle. And that's going to go on top of the iron ring. So a clay triangle is going to be a triangle behind there. There's my triangle. And then it just like supports the three edges right there. So basically, this is a bird's eye view. Clay triangle would be on top of it. It's supported by these little wires, little metal on the outside. And then on top of that would be the crucible that would sit right in the middle. Then obviously you have the little sulfates. Copper sulfate in there. But anyways, strike your Bunsen burner. Going through this process, you'd have a flame coming out. I'm gonna magnify a flame. So let's do a Bunsen burner quick at the top. Let's magnify that. Do that over to the left. So here's my Bunsen burner, just the top of the Bunsen burner. I zoomed in on that. So a flame, there's gonna be two different cones of a flame. You light that flame, what's going to happen, there's going to be a outer cone of the flame, it's red fire, and then there's going to be like an inner cone of the flame. So outer and an inner, oops, should be symmetrical. Outer and an inner portion of the flame. So when you're analyzing a flame, if they were to ask you to heat something vigorously or quickly, then the hottest part of the flame is going to be the apex, the top of the inner cone. So this portion right here, that blue, there's going to be blue flame there. That top right there is going to be the hottest part of the flame. If it says to slowly heat it, you want to heat it at a higher distance away from the inner cone. So obviously a flame, two different colors you're going to see on it from a Bunsen burner. Definitely going to have that red or orangish color, but that blue or violet color is going to be on the inner portion of the flame. So that is supposed to be a Bunsen burner with a flame. Hottest part, not as hot. All right, so back to the drawing board for my apparatus, the stand, iron ring, all that stuff. after you heat this thing on up, what's going to happen is that the water, that H2O, is going to start to evaporate. It's going to start to evaporate from the CuSO4. So as you heat it on up, turn it on up, the water is going to start to escape. And what's going to happen to the particles down here? They're going to start to lose their color, that blue color there. They're going to start to go from a light blue. And then after, if you heat it up enough, it should have a white particles all remaining. So like kind of like table salt at the end. You know if you got rid of all the water by the change in color. So after it changes color, you can figure out that there's not much left, and you can figure out how much you lost, how much water was stuck in there. So you'd start off with a crystal. Inside that crystal, there's gonna be little waters in there. You'd break down the crystal to fine powder, heat it up, and then you have the hydrate extracted there. But let's do a little bit more and watch a flick on that too. Any questions on that weird drawing? Try my best in my drawings. All right, to determine percent of water in a hydrate, what you have to do, you have to divide the formula mass. Divide the formula mass. Of the water. In the hydrates by the total GFM. So again, it's going to be very similar to what we did last time with GFMs here and percent composition by the total gram formula mass. Of the hydrate and multiply it by the last digit of 100. So multiply it by 100 again. Before I go through this example, I'm going to play the flick on a hydrate. It's a few minutes long. They're going through a laboratory demonstration or experiment of how to actually extract the water from a crystal. So I will play this. It is like 12 minutes long, but I'm going to speed it up a little bit because it does go a little slow by YouTube playback speed.
All right, let's go ahead and get started. We're in the laboratory today. We're going to be doing a laboratory called the percentage of water in a hydrate. So I guess a good place to be to ask the question, what is a hydrate? Well, a hydrate, the one we're going to be using today, is called copper 2-sulfate pentahydrate. This is a beautiful blue crystal, and see, it's a very deep blue color, and it contains water. In fact, every formula unit of copper 2-sulfate pentahydrate contains 5 molecules of water. And so it's going to be our job today to experimentally determine the percentage of water in a hydrate. We did this in the lecture in our notes, but what we want to do today is compare what we got in our notes to what we're going to get experimentally to look for any kind of error that may have occurred between what we calculate and what we actually do in the laboratory. The first thing we're going to do is we're going to get a measurement or get a mass of a crucible. And a crucible is just a small vessel, a ceramic vessel just like that. It is able to withstand a large amount of heat. We're going to be heating up the copper 2-sulfate pentahydrate. Now I'm just going to place it onto the scale. I previously balanced the scale. And the scale, by the way, should be measured up to a 1/100th of a gram. In this case, I get 12.51 grams. So I'll record that 12.51 grams as the mass of my crucible. The next thing I'm going to do is I'm going to place a small amount of the copper 2-sulfate pentahydrate onto into the vessel, the crucible. I'm not going to use that piece. I want to use a much smaller piece because it'll be a lot quicker and I'll be able to get a measurement a lot faster. So what I'm going to do is place a small piece of copper 2-sulfate pentahydrate into the crucible and I'll measure once again. And this time I get 12.70. So 12.70 grams for the mass of the crystal and the crucible before heating. So the next thing I need to do is set up the apparatus for heating. The ring stand is already set up for me. In this case, I've got a ring clamp. All I need to do now is to add a clay triangle. So clay triangle will just prevent or allow the heating of the crucible to take place, and it'll provide a platform that I can place the crucible onto. So just make sure that it's steady, it's stable, and there's nothing that's going to move around during the experiment. So, by the way, the ring stand or the ring clamp should be about 2 or 3 inches, 3.5 inches at the most, away from the exit from the flame of your Bunsen burner. There shouldn't be any obstructions. Everything should be out of the way as you start the flame. make sure that as you approach the apparatus, that the Bunsen burner or the lever is at a 45-degree angle, indicating that no gas leakage is occurring. There's no impediments to gas flow in the tube itself, and that we should have a good flow of gas into the Bunsen burner. So we'll just take a match and start our Bunsen burner. Remember, when you light the Bunsen burner, you always start the match first, just like that. Now I'm going to make a C with my body, just like that. I want to maximize the distance between the match or the flame and myself, and then I'm going to, with my opposing hand, just start the flame just like that. Just slowly start the flame, and it catches pretty quickly, just like that. I don't need a terribly hot flame, so I'll back the flame up quite a bit. That's fine. That's more than enough right there. So the next thing I'm going to do is I'm going to start the warming of the copper 2 sulfite pentahydrate. Be very careful because of the fact that there's quite a bit of heat being generated by that flame. So you want to make sure that you respect the amount of heat that ceramic vessel, that crucible, is able to absorb. So don't pick it up with your fingers by any means. It may not look hot, but believe me, it's going to get hot in just a few minutes. So the next thing is just to wait. And it'll take just a few minutes for my little copper 2 sulfate pentahydrate crystal to desiccate, or the water to leave the crystal. You'll see some noticeable changes, and I'll show them to you on the video in just a moment. But for right now, I think the best thing to do is simply wait and just give it a few minutes. Allow the copper 2 sulfate pentahydrate to lose its water in the heat. I'll just turn it up just a bit, just like that. Here we go. And as I do that, I hear a little bit of sizzling, and I see some changes. You can't see this, but I will just tell you that the copper 2 sulfite pentahydrate is losing that beautiful blue color, and it's just turning white. And I'll just use my glass stirring rod just to move it around just a little bit so that it doesn't get caught in one place. Okay? So there's going to be quite a bit of waiting in this laboratory, both waiting to heat it up and also waiting for it to cool down, because you want to make sure that it's cool before you place the crucible back onto the weighing station or the balance. So it's really starting to get white now. I'll show you that again in just a little while. And it's even starting to crumble. I'll just do that just a little bit. And it's really starting to fall apart. Okay, it's not going to take much longer. If you use a small enough crystal, it shouldn't take more than 2 or 3 minutes. But you'll know that you're done when the crystal completely falls apart. It should look like almost like ash. Okay? It's really starting to fall apart now. Be careful now. That flame is very hot. And I'll just give it a few more minutes. Okay, the key again is there's no real advantage to using a large crystal. So don't pick a large crystal out of the container that you're given. Try to find one that's not so large. You'll get the same exact results that you would have if you used a larger crystal without having to wait nearly as long. So this crystal that I have here is nearly completely disintegrated now. That blue color that we saw before is now completely gone, and I'll show you that now in the video. So I'll take it off the flame. I'm going to go ahead and turn the flame off now. There's no point in having it on while I'm waiting, while it's cooling. And I don't want to take a chance on getting injured or having someone be injured. But I hope you can see that on the video. The copper 2 sulfate pentahydrate, again, has lost that color, and it's now very much a white ash type of looking material. So I'm going to give that just a few minutes to cool down. Be careful about putting it on paper or any other surface that you don't want to burn, because it is very hot. Okay, so we'll give that a couple of minutes just to cool down. And while we're doing that, we're going to do a couple of calculations. One of the calculations that we want to do is we want to make sure that we know how to do the calculation for determining the amount of water in the copper 2 sulfate pentahydrate. So there's some questions on the back of the sheet that require that we do that. This particular one has 5 waters. It's a pentahydrate, so it has 5 waters. It would be to your advantage to memorize that water has a molecular weight of 18.02. It's 1.01 for the hydrogen. Twice that is 2.02. Add that to 16 for the oxygen, and you get 18.02. By the way, you should have a calculator handy for this particular experiment. I've got one here, so I'm going to do the calculation very quickly. We have 18.02 times 5, because there are 5 of these water molecules, so that gives me 90.1. So 90.1 then is the mass of just the water alone. So I'm in the process of cooling this down. I'm getting experimental data, but I also want to compare that to calculated value. So 90.1 is the mass of the water. That's the calculation that I get. Now, we want to compare that in percent water, because percent means part of a whole. We want to compare that to the copper sulfate pentahydrate. In other words, the whole molecule. So we have copper, which has an atomic mass, or average atomic weight of, so I'll look up copper, 63.55 for copper. Sulfur would be, so find sulfur on the periodic table, 32.07 for sulfur, and then oxygen would be 64.0. Why 64.0, not 16? Well, remember in the copper 2 sulfate pentahydrate, the formula is Cu, that's for copper, S for sulfur, O4. So there's a 4 subscript on the oxygen, so you're going to have to multiply the oxygen 16 by 4, or 64. So when we do that, we add that up, we get 159.62. So you can just add that up on the calculator, 159.62. So remember, we're comparing the water alone to the copper 2 sulfate pentahydrate, which is 159.62 plus the water. That's the entire molecule. So we get 90.1 divided by 159.62 plus 0.91. Let me do that calculation very quickly. And I get 36%. So at least theoretically, my theoretical yield for the water, the amount of water theoretically that I should get, will be 36%. So we'll see what happens in just a moment, and we'll calculate or determine how much water left the hydrate experimentally and compare that to what we get in our calculation. Okay? Now, I've been talking for a few minutes, so be very careful as you touch the crucible. You don't push it hard, but you can determine just how hot it is. Okay, I can see that this crucible is pretty hot, and I'm just not sure that I would want that on the balance. So I'm going to wait just a few minutes before I put it onto the balance. I'll move it over here, just so it's a little bit closer to the balance when I get ready to move it. So I'll move it right there. Okay. One of the things that we're going to want to do, be careful with this as well. One of the things that we're going to want to do is to calculate the percentage error. Okay, the percent error. So make sure you know how to take experimental data and take data that we got in the laboratory, or take data that we got in the laboratory and compare it to data that we calculate. Okay? All right, I think that's just about ready to be moved over to the scale, and we'll get a second reading. Okay? So this is the reading after heating. Okay, this is the amount or the mass of the pentahydrate after the heating. And what I get this time is 12.62. 12.62. So a bit lighter than before the heating, 12.62 grams. The next thing I'm going to want to do is I'm going to want to heat this a second time. I won't do it on video because it'll just take up extra time. But you know what I mean when I say just heat it up a second time. Go through the same procedure. Make sure that the gas is turned on and there are no problems. Heat it a second time because you're going to want to make sure that every little bit of water has exited that decahydrate, or the pentahydrate rather. So that should do it for this laboratory, percentage of water in a hydrate, and I'll see you next time. Thank you.
All right, he did a pretty good job going through that lab. Again, that's one of the basic labs that you should be aware of when you take Regents chemistry. So when we get back to school, if the time comes, we'll definitely do that one for review. Hopefully you now understand how to do that step. All right, let's do 2 examples and let's get you out of here. So example number 1. I'll put it all on the same page, so I'm going to press enter a few times. Example number 1, here we go. A 10.4 gram sample of a hydrated crystal is heated to a constant mass of 8.72 grams. Calculate the percent of water that was in the hydrate. So going through this, highlight the important information. We have 10.4 gram sample of hydrated crystal. Color that blue. Was heated to a final temp of, or final mass, after it's heated, to 8.72. Calculate the percent of water that was in the hydrate. So we want to know how much water was in that hydrate. So I'm going to go through some information over here to the left. I have the mass of the hydrate. Mass of hydrate is equal to 10.4 grams. Mass of hydrate is equal to 10.4 grams. Whoops. We have a final mass after it's heated on up. So I'll call this mass final. It's 8.72. And what we're looking for is percent of water in the hydrate. So those I drew out from the passage, the question. The formula you're going to have to use here is going to be the same as the percent formula. So it's going to be the percent formula. It's going to be part over whole times 100. Percent composition equals part over whole times 100. Let's take some time to get there. Press tab, it's going to bring a new cell in there. That chair is squeaky. It's not me. Uh-oh. All right, so the formula is percent equals part over whole times 100. It doesn't have to look exactly like mine. Hopefully you know where this formula comes from. That is given to you on the reference table. Okay, so let's go through this. Let's think about this process again. We want to know how much water was in there. We want to know how much water was in there. You start off with a crucible. You start off with some crystals in there. I'll say it's my before picture. This is my after picture. And you have some blue crystals in there. This has an initial mass of 10.4. So this mass is equal to 10.4. After you added some heat to it, so then you heat it on up. After you heat it on up, there's my fire. After you heat it on up, you had a final mass. Not as great as a mass, so I'll make it a little smaller. And that was equal to 8.72. How much water was in there? How much water was in there? Oh, sorry, Leonardo. Y'all scroll up. I haven't seen that message in a while. It's from a while back. I'll go back to this question. Leonardo, I'll go back up in a second. Well, I don't get it. I'm reading my chats from now. Mr. Brown, you're shape shifting into animals. You saw my. Oh, great.
Oh yeah, we saw the whole thing.
Oh yeah. Hope I wasn't picking my
Yeah,
nose.
we couldn't even see the video. We just saw
What? Are you kidding me?
you.
The whole time?
Except for like the last 20 seconds, yeah.
Oh my god. For real? Oh man. That's great. So you guys didn't tell me you didn't see the video. You just saw me being like a pig, and that's great. Sorry about that. Wasted 10 minutes of your life, folks. Traveling the world, yeah. Being in the grass, all that good stuff. Gangster? The gangster look? Oh man, I'm ready to cancel class the rest of the day. Anyways, moving on forward. Let's get back to this. Hopefully you heard the video. Last 20 seconds, whatever. All right, to figure out the Lena, I still go up and back in a second. To figure out how much mass of the water was in there, you have to subtract 10.4 by 8.72. 10.4 by 8.72. Subtract those two right there. It's going to give you the part. So my part is going to be, so I'm going to copy that formula. So no, next time not to play with my video features. I was trying to figure out how to get, honestly, this is what I was trying to do. I was trying to get the caption. So when I talk, you could get the captions there. Then I just lost my focus. Probably like you guys do all the time. Some classes, maybe my class, hope not. All right, so the part is going to be subtracted. You're subtracting 10.4 minus 8.72. You subtract those two values. So I'm just going to put 10.4 minus 8.72. The whole is going to be the initial. The initial is going to be 10.4. I really wish I read those messages before, but they were hidden. So now we can go through and figure out this equation or the percentage here. Copy that again, and paste it again. And then obviously 10.4 minus 8.72 would be 1.68. Calculate what's the percent of water that was in that hydrate? Anybody? Please calculate the percent of water that was in that hydrate. Thanks, Joseph. Percent of water was 16.2%. So 16.2%. Obviously, if you watched that video instead of watching my video filters, you would have saw that as well. And we'll do this in class. It'll be easier to think about, to interpret when you actually do the experiment too. So there's the first one. On a lighter note, you guys asked what I was doing yesterday. How's my day yesterday? Fine, I'll tell you how my day was yesterday. Fine, all that snow. Told you snow was coming. You guys saw a little bit of me there. Played outside in the snow a little bit. Hopefully you got a chance to go outside, enjoy that weather. Picks. Here's what I did yesterday. That little guy.
Oh,
There's one of them.
Watch,
Watch that screen. Ready? Yeah. Oh. Here comes my wife and daughter.
Whoa! How was that, guys? Good times. Nice job.
Oh my god, we went fast. Let's do it again.
Woohoo!
Let's do it again. There we go. Yeah, go for a sled. Go down the parkway. Go find a hill. Just go out there, have fun. That was my day yesterday. Thanks for asking. All right, back to the next example. Let's go. Let's finish up the last example and let's get out of here for the weekend. It's fun. All right, next example. Here we go. It says, what is the not Father Dear. What is the percent composition by mass of each element in CuCO3 with 2 moles of water trapped inside? So we have this compound. We know water is trapped inside now because that little dot right there means something's trapped inside. You're only going to see it with like water trapped inside. So it's not going to be like that and like NaCl mixed in there. That dot means water is trapped within an ionic compound. It's going to be trapped within an ionic compound if that dot's there. It can't be covalent. It will be an ionic compound. So what's percent by mass of each element in CuCO3 with 2 moles of water? So this situation, what you're going to do first is going to find the GFM. I'm going to add another cell here. I'm going to solve for the GFM, and then I'm going to calculate these, and that'll be pretty easy. Then you're out of here for the weekend. So I'm going to insert a new cell. When I press tab, it doesn't do that now, but I want a cell right here. So if I click there, if I right click my mouse, it allows me to go insert cells. I'm going to insert above. So if I have a Chromebook, I'm going to put 2 fingers down at the same time on my keypad. I'm going to insert row above. This is going to be my GFM, gram formula mass for Cu, that compound up there. So we're looking for the GFM of this entire thing. GFM for this compound. Again, that's first thing's going to be the ion. Then you're going to have the number of moles, hashtag moles. Then you're going to have the mass of the ion. That's the setup for GFM. The first ion we have here is Cu. How many moles of Cu are present there? Throw in the chat or on mute. How many moles of Cu are present there? What's the mass of Cu?
1.
Thank you. What's the mass of Cu? Throw in the chat or on mute, please. Thanks, Alan. So mass C, you can find in the reference table. Hopefully you have a reference table handy. 63.5. Cu, 63.5 is a mass of Cu. Yep, 63.5. Multiply those together, we get 63.5. Next up, how many moles? Obviously, you know there's 3 moles. I think you know that. 3 moles of CO. The mass of CO. Find the reference table. CO, element number 27. Mass is going to be equal to 58.9. Three times 58.9. 176.7. Next up, you also have to account for the water. How many moles of H are there? Anybody? How many H's are present there? Not two this time. How many moles of H? If you check it out, there's gonna be 4. That 2 is gonna transfer on over to there. So there's gonna be 4 moles of H. The mass of H is 1.0. Obviously, it's gonna be 4 times 1, which is gonna give you 4.0. And the last one, how many O's are present there? Thanks for playing, SC. There's 2 moles of O. Mass is 16.0. The more you use these values, the quicker you'll know these values as well. So that's going to be a GFM of 32.0. Last thing you have to do for the total GFM is add them all together. So add it all together. If I didn't make a mistake, I got a GFM of 276.2 units or AMU, atomic mass units. Total GFM equals that. My total GFM, 276.2. Now I think you can do the rest of this. Once you figured out there's 2 moles of water trapped, then you can figure out the percentage of each of these elements in this compound with water trapped in there too. So we know the formula is going to be part over whole times 100. I'm going to color code these just so you can follow the flow. I'll make this one blue. I'll paint it all. So I'll take my time writing this one, and then the rest of them are going to be really easy. So the percent composition of Cu, it's going to be part over whole times 100. The part is going to be 63.5. The whole is the total GFM, including the water there as well. So the whole is 276.2. What's the percent of Cu in this compound? Anybody? Percent of Cu in the compound. Please tell me the percent of Cu in that compound. Thank you, Alan. 23%. Hopefully you all got 23.0% as well. Thanks, Mike. All right, once you have that one down, now the rest of them, I'm just going to copy this format. I'm going to replace a couple things for the rest of them. So next one's going to be cobalt. I'm going to copy paste it down below. I'm going to tweak up the formula a little bit. So instead of CO, it's Cu. Instead of Cu, it's CO. So now we're analyzing cobalt. The mass of cobalt is 176.7. So I'm going to switch that out. 176.7. The total GFM did not change. What is the percent of cobalt in the compound? Please put in the chat once you derive an answer. All right, Joe. Thanks, Faith. Thanks, Steve. Yes, 64. 2 people got 64. 64.0 is my percent. So 64% of the compound is cobalt. 23% is going to be copper. The remaining is going to be devoted to water. So I have to do the same thing for H and the same thing for O. All right, so again, I'm going to copy my last formula that I had there. Should already be copied in there. And paste it on in below. Look for percent of H. The mass is going to be different. It's going to be 4. The GFM's the same though. What is a percent of H when you're ready? Thanks, Asim. Thanks, Faith. 1.4. So 1.4% is going to be H. And last but not least is O, oxygen. We're doing the same thing for oxygen as well. Oxygen. Substitute the values for oxygen. Percent of oxygen, the part we already figured out the GFM for oxygen. Oxygen, we said there's 32 per mass. Please calculate the percent of oxygen in the compound. Thanks, guys. 11.6%. So again, if you add all these together, all the percentages together, we should get something really close to 100, maybe 99.8, 0.7, or 100%. So yeah, 11.6% is the last one for oxygen. Hopefully you know how to calculate those. Hopefully you now know what my video filters I like. Hopefully you can go through that as well. Forgot to trap the water inside a compound. But there is the class today. Next class, we'll be going over types of chemical equations. But that's it for today. Have a great weekend. Do not forget to do topics number 5 and topic number 6 for the exit passes. If you have any questions, feel free to hang out for a few minutes and I'll definitely address them. If you don't, have a great day. Have a good weekend. Stay safe, stay healthy, and we'll see you guys later. See you later.
Have a great weekend, Mr. Brown.
Thank you.
Have
You
a good
too.
weekend.
All right, we'll see you guys. Thank you. You too. Bye, Kai. Bye, Ellen. Bye, Nadina. See you, Kim. Bye, Steve. Have a great day, guys. We'll see you.